Welcome to today's webinar, Running Microservices on Amazon ECS. Our presenter today is Pierre Steckmeyer. Pierre is an AWS solutions architect with a background in tech ops for the finance industry. He gets excited about technology shifts like containers, serverless architectures, 3D printing, blockchains, and more. Today with us, we also have Daniele Strupa, Product Marketing Manager, and Andrew Thomas, Product Manager for ECS, as our webinar moderators. They will be engaging with you and answering your questions throughout the presentation while our presenter presents. Pierre, welcome. The floor is now yours.
All right, thank you very much, Ryan. Hello, everyone. Thank you for the introduction again. I'm a solutions architect in New York City, and my subject matter expertise is in EC2 container service. And I'm here to talk to you about EC2 container service, and more specifically, why and how to run microservices on ECS. I'm really excited to present to you today, and I just want to get into it right now. So in this session, we will first discuss the concept of microservices, what they are, their benefits, and how they differ from other architectures. We will then talk about some challenges that you might face when working with microservices, and we will see how Amazon ECS can help tackle them. It's relevant to note that even if you are not building microservices with containers, a lot of the design principles we will talk about are broadly applicable to the cloud architecture in general. Because basically things like the ability to scale and decoupled architectures are critical to any successful cloud architecture. All right, number one, microservices. If you go on the Wikipedia page, here's what you will see. The microservices architecture is a design approach to build a single application as a set of small services. Each service runs in its own process and it communicates with other services via a well-defined interface using a lightweight mechanism, typically HTTP-based application programming interface, API. Microservices are built around business capabilities, and each service performs a single function. Microservices can be written using different frameworks or programming languages, and you can deploy them independently as a single service or as a group of services. Now, how does that compare to other major architectural patterns? Well, Monolithic is probably the most clear-cut here, and I would expect most of the audience to have experience with this sort of application architecture. If we go with the semantics, monolith originally means single large piece, and the whole application is in this one single unit. All the business logic is contained within this one unit. Everything is tightly coupled. If you change the functionality in one part of the application, you will probably have to test the functionality of the entire application, which means that you'll have to also build the entire application. But prior to building, you will need to agree with other teams on merging, which version of the code do we need to assemble together. Also, resources are usually shared. This is true for the backend, the database, but also the memory on the host for inter-processes communication. The next step towards microservices is really a service-oriented architecture. Here, the application is broken down in a few sophisticated components. However, the business logic can live across domains. For me, it's really common to associate service-oriented architecture with some form of middleware, like an enterprise service bus, underlying to most of the components. And this generally implies a higher degree of coupling. So still, a change in one part of the application triggers testing across multiple parts of the application. And this can be time-consuming. Now, more recently, the discussion has revolved around microservices. And in this case, the application is composed of many very small microservices, very small components, sorry. Each component exposes an API that abstracts whatever language or data storage is behind the endpoint. The business logic tends to live inside a single service domain. So as long as you don't break functionality on your API, If you make a change to the service, the test can just verify functionality of that one service. Now, these microservices will communicate with each other via simple wire protocols, again, like HTTP with maybe XML or JSON, and they're API driven. So why would you want to move away from a monolithic architecture in the first place? What are the challenges here? Well, the main challenge is giving sub-components a degree of autonomy. This could include limiting the dev teams from developing the new features that they want to deliver at their own pace. They could be waiting for other teams to finish and merge an associated change. And it might be impossible to change one component without changing another one. So there's a degree of slowing down the agility and reducing your capacity of innovating. Another sticky point is scaling. If you were to run a monolithic application on AWS, you would probably wrap your application in a WAR file, a Rails application, or something similar. Right? And one part of the application might be CPU intensive, another one might need a lot of memory. But you cannot break those into appropriate fleets underneath. You would have to run it on an EC2 instance type that would meet the need of all of your application. So to scale the application, you would replicate it on many instances, typically using auto-scaling. And to scale back in, you would do the opposite. It limits your flexibility, and it makes it difficult to have efficient resource utilization. But people started writing applications differently. Many customers were splitting each component into its own microservice. And you can place these loosely coupled components onto their own set of underlying instances. This makes it possible to scale each service independently on its own fleet. This pattern is really natural for the cloud. You can have different auto-scaling groups, different instance types, different launch configurations, and you can scale each service on the metrics that make sense for each of those. In our example here, maybe the user service is the part that receives the most traffic, and you can scale this one component. You can scale it appropriately. If the shipping service is less stressed, then it does not need to be scaled as much. And that helps you track resource utilization in an efficient and targeted manner. So if I had to summarize a few important characteristics of microservices, this is how I would do it. With microservices, you can do one thing well. Microservices are organized around business capability, and teams need to take care of all aspects for that business area, including the user interface, persistent storage, and any external collaborations. Each service team is also cross-functional, including the full range of skills that are required for development, of course, right? But also user experience, database, project management. With microservices, each team owns a product over its full lifetime. And this helps bringing developers in contact with how their software behaves in production, in real life. It also increases contact with their users, as they will support their service. So the team gets to build and run their product. There's also a degree of independence. So each microservice can be independently deployed and redeployed again without impacting the overall system. This allows for each service team to move at their own pace, introducing new features and versions as fast as they need. So there's no more waiting for another team to merge their own part. And it bears repeating, these services will also scale independently. Each service team have the freedom to choose the best tool for their specific problems. As a consequence, microservice architectures are usually heterogeneous with regard to operating systems, programming languages, data stores, and tools. This is an approach that is called polyglot persistence in programming. Rather than sticking to a common set of tools and standards, each service team has the freedom to produce useful tools that can be used by others to solve the same problems. In a similar way, microservices also decentralize data storage decisions. Each service team manages its own database, either different instances of the same database technology or entirely different database systems. And then there's also the concept of black box. Each service publishes an explicitly defined interface and honors it at all times. The consuming services only care about that interface, that part of the service, and they should not have any runtime dependency on the consume service. Services agree upon a specific contract, and they communicate using only that. The exposed API is a contract. As long as you're maintaining this, it frees you up and turns your service into a black box. So this sounds great, but of course, embracing the microservices approach comes with its set of challenges. We have identified resource and state management, monitoring, service discovery, and deployment. These are not microservices exclusive problems, by the way. With cloud architectures, in general, there can be an increased deployment and operational complexity when the scale gets really large. It's important to work through these challenges and to try to address them. Right, so let's start with resource and state management. This is also often referred to as orchestration. Basically, what it means to be is, how do I know what resources I have available? What states are they in? And how do I make sure that it is all configured that the way I want it? There are a lot of distributed things and a lot of stuff I have to control. So why is Amazon EC2 Container Service the right thing to talk about when addressing resource and state management concerns in microservices architectures? Well, we built it for running containers at scale across clusters of EC2 instances. So maybe this is a good time to take a step back and understand how containers fit in the whole microservices picture. Containers and Docker in particular are natural for this architectural pattern. Containers make service simple to model. The application and all of its dependencies are packaged into an immutable image using a Docker file. Inside that image can be any application, any language. And that's the black box component that we talked about. The image itself is a versioned artifact that can be stored in a repository, just like your source code. That makes it easy to understand which version of the image corresponds to which version of my code. It also makes it easy to test and deploy your applications because, well, they are the same artifacts. Deployment is also made easy. So you start using stateless servers, which are natural with Docker, and each deployment is just a new set of containers. The risk of change is decreased, and rollback is very simple. In summary, the containers make it easy to decompose applications into microservices. Each microservice is self-contained, allowing you to reduce dependency conflicts and decouple deployments. A couple of years ago, after talking to customers, we realized that the big problem that they faced when they were adopting Docker is that it was actually pretty easy to run a handful of containers, and for this the Docker CLI is very powerful. But running applications in production at a certain scale was a much bigger challenge. All of a sudden, they had a lot of questions to answer. What instances have the available resources that my service needs? Like, for example, this much memory and this TCP port. How do I know if a container dies? And what do I do about it? How do I hook into other resources, like a load balancer or an identity and access security service? How do I efficiently deploy a new software? How do I grow or shrink my infrastructure? So you see a lot of questions that we wanted to help answer. So let's touch on a few components of ECS about how it works before we start diving into implementation details. So Amazon EC2 Container Service is a highly scalable, high-performance container management service that it supports Docker and allows you to easily run applications on a managed cluster of Amazon EC2 instances. It allows you to make containers a foundational building block for your applications. At AWS, we want to make them first-class citizens. The idea is to give them full functionality equivalent to Amazon EC2 eventually. So the service eliminates the need for you to run and manage a cluster manager or configuration management system by providing you programmatic access to the full state of your cluster and allowing you to schedule containers based on your application requirements. It's based on some primitives that we developed internally for managing some very large-scale clusters. And all of that is exposed through a simple set of APIs. You get full visibility and control over all the resources that are in the cluster. So what do we mean when we say highly scalable? This should give you an idea. We ran a few load tests on ECS. And in one of them, we scaled our cluster over a 3-day period from about 200 instances to over 1,000 instances. And this is what you see as the purple line here. The green and red line show the P99 and P50 latencies. So as you can see, they're relatively flat, and that demonstrates that ECS is stable and will scale regardless of your cluster size. We can provide detailed state tracking even if your cluster is very large. All right, let's talk about container placement. In other words, scheduling. ECS has 2 schedulers to find instance placement based on resource needs, isolation policies, and availability requirement. So what do these schedulers do and why are they important? Well, a scheduler understands the needs of the system. The work that needs to be done, such as starting a container that needs 200 megabytes of memory and TCP port 80. And it looks to efficiently satisfy these needs. Then it submits a request to the cluster state manager. Since ECS provides optimistic concurrency control, multiple schedulers can operate at the same time. The cluster management confirms the resource availability, and then it commits to the scheduler. The scheduler can then listen for events from the cluster manager and take action on it. Such events could be information pertaining to the availability of applications, for example. You do not have to use the ECS schedulers. You can actually write your own, and you can do so by using the available APIs. Amazon ECS is built to work with the AWS services that you value, that you're familiar with. You can set up each cluster in its own virtual private cloud and use security groups to control network access to your EC2 instances. You can also store persistent information using Elastic Block Store. And you can route traffic to containers using Elastic Load Balancer. CloudTrail integration captures every API access for security analysis, resource change tracking, or compliance auditing. Now let's get into a bit of terminology. What do we call a cluster? Well, a cluster is a collection of resources, primarily instances and containers. You can have instances from multiple availability zones in your cluster. It's just a big bucket of resources, CPU, memory, etc. It's also dynamically scalable. It's possible to have a 1-instance cluster or a 1,000 instance cluster. And the clusters can be a good way to segment your resources for particular purposes. You could have a development cluster, a test cluster. You get the idea. On a cluster, you can run tasks. In ECS, you model your applications by creating a task definition. The task definition is a JSON document which details which container images to use, how the containers are going to be linked to each other, what resources they need, etc. So you can think of it as an equivalent of Docker Compose, let's say. A task is an instantiation of a task definition. You can have a task with just one container, or up to 10, that will work together on a single machine. It could be Nginx in front of Rails, or Redis behind Rails. And you can run as many tasks on an instance as will fit. One quick note, often people wonder about cross-host links, and these don't go in your task. You can put them behind an ELB or a discovery system and make multiple tasks. Services now are a higher level construct than a task. They allow you to run and maintain a specified number, what we call the desired count, a specified number of instances of a task definition simultaneously in an ECS cluster. If any of your tasks should fail or stop for any reason, the Amazon ECS Service Scheduler launches another instance of your task definition to replace it and maintain the desired count of tasks in the service. On top of maintaining this number of tasks in your service, you can optionally run your service behind a load balancer. The load balancer will distribute traffic across the tasks that are associated with it. The next challenge that I want to talk to you about is monitoring. Monitoring is a key component in your infrastructure. But when you have hundreds of services, it can become challenging. So what are some approaches that you can take to handle this? Well, first is the fact that Amazon ECS provides a number of metrics for your clusters and services. These are reservation metrics and utilization metrics. Reservation metrics are measured as the percentage of CPU and memory that is reserved by all Amazon ECS tasks on a cluster. Similarly, utilization is measured as the percentage of CPU and memory that is used by all Amazon ECS tasks on the cluster. Now, utilization metrics are available for two dimensions, at the cluster level and at the service per cluster level. And these metrics are collected once a minute, and they're stored for a period of 2 weeks. This is what these metrics look like. They are available on ECS, on the Consul, but also on CloudWatch. CloudWatch is the monitoring service for AWS Cloud Resources and all the applications that you run on AWS. You can see here that we display them as a chart, but you can also define alarms based on their value. So let's clarify utilization versus reservation. When you run a task, you specify how much memory is reserved for its containers. So if you have 3 containers and each of them needs 100 megabytes, you would have 300 megabytes of reservation across your cluster. However, each one might only be using 20% of the memory at any given time. And that's the current utilization. So both are useful in understanding how much is available for placement and how much is actually used in your cluster. You now know that we offer 4 cluster-related metrics. What if you want to add your own set of metrics, such as disk space? Well, you can do so by making use of the put metric data API call, or calling a script like the one that you see here. These scripts are described in the CloudWatch documentation, by the way. Amazon CloudWatch associates the data points with the specified metric. If that specified metric doesn't exist, it will just create it. The result is that you can add the monitoring metrics that best fit your needs. Now, you don't have to use Amazon CloudWatch. There are other solutions in our partner ecosystem, and I wanted to just discuss 2 of them today. Datadog is purpose-built to monitor highly dynamic infrastructure, including containers. It understands the difference between pets and cattle. And what I mean by this is that traditional name servers, usually physical, versus dynamically created virtual machines that go up and down very frequently. So when ECS brings new containers online, Datadog automatically begins tracking their metrics. When the containers go offline, Datadog handles that gracefully. But if your Docker deployment has service level problems, the service will notice and send you alerts. I'm talking about Datadog. So the Docker metrics can be viewed individually in dynamic groups or correlated with metrics from the rest of your infrastructure. Not only can Datadog track your containers, it also can track what's running inside of them. It has over 100 built-in integrations for standard software and services, and it can track your custom applications. Another system that you might be familiar with is Sysdig Cloud. At a high level, Sysdig Cloud offers two things. By extracting metadata from Docker and ECS, Sysdig allows you to visualize the logical topology of your microservice application, showing the physical hierarchy or grouping containers into tasks and services and ignoring their physical location. This information is combined with Sysdig Container Vision technology, which makes it possible to inspect applications running inside containers without requiring any instrumentation of the container or the application. Another feature that they have is the ability to do a historical replay of your container, the whole container lifecycle, and this can be very useful for troubleshooting. So you get a nice level of visibility from both an infrastructure and an application point of view. On to our next challenge. This time is service discovery. Now, this is a key component of most distributed systems and service-oriented architectures. The problem seems simple at first. How do clients determine the IP and port for a service that exists on multiple hosts? Well, back before cloud computing, it was more acceptable to have statically addressed resources. For example, you knew where your database server was. It had an IP address that was static, a reservation in your DNS. If any of that changed, it could cause a problem, but it would be manually resolved. Nowadays, this kind of change is considered a constant. Cloud architectures are highly dynamic, and this is very much applicable to containers, which quickly spin up on any host, get an IP and port assigned, and live for a short amount of time. Then they might get spun down, respawn on another host with a different IP and port. And you need to be able to find this service wherever it might exist. So one answer to this challenge relies on AWS primitives, leveraging elastic load balancing and CNAMEs. You would use a single ELB per service. And this is a solution that is used by the company Remind in their self-hosted platform as a service built on ECS. They call the whole solution Empire, and it is open source. They opted to use a private hosted zone in Route 53 and create CNAMEs. These CNAMEs point to the ELBs for each application or web processes. They also use DHCP option sets to set the search path on a host to .example or .mycompany. So the services need only know the name of the app they want to talk to. This is how it looks like from an architecture point of view. So you can then run an application router, basically Nginx, and route to the appropriate private applications, whether that is the API, a web dashboard, or another service. It also handles request ID generation, so you can trace requests as they move from service to service. You can also use ELBs in a private subnet if you want these ELBs to front backend only services, for example. Another option to provide service discovery to your microservices is through the use of Weave. Weave is a great option, and it's pretty intuitive. It provides a DNS interface for a cross-host container communication. If I were to summarize this, the way that it works is that Weave allows you to reference containers by their name, like you would locally with Docker links across the entire cluster. It doesn't use an external database or a consensus algorithm, but instead it uses a gossip protocol to share grouped updates about what's running on each host. And it also provides load balancing via response randomization. So how does it actually work? Well, it's made up of a few components, and they all run as containers across a cluster, of course. One is the Weave proxy, and this sits between the ECS agent and the Docker daemon, intercepting the communication between the two. It automatically attaches containers to the Weave network and assigns them an IP when they're started. Another component is WeaveNet. WeaveNet implements an overlay network between Docker hosts. So each packet is encapsulated in a tunnel header and sent to the destination host. Now the packet goes straight from the user's application to the kernel, and WeaveRouter uses Linux kernel's Open vSwitch module to tell the kernel how to process packets. This makes Weave very fast and low latency, despite being an overlay. Weave chooses a random subset of peers with which it will exchange topology information. It also creates a network bridge on the host. Each container is connected to that bridge via a virtual Ethernet pair. And then Gossip, as I said, is used to share the topology across the cluster. So it turns out that key value stores are another really good option for service discovery. And this is the principle that HashiCorp's Consul is built upon. We implemented this solution in our reInvent bootcamp last year. It works very well. Consul works by essentially maintaining a cluster of servers and clients that communicate over Gossip, again, but using Raft as the consensus algorithm. You end up with a highly available key value store, which allows you to correlate information like host names, IP ports, or anything that you would want to save in a key value store. So let's look at the architecture. Consul has also a few moving parts that are required to make this really dynamic. On each host, you need the Consul server or a client, so the host partakes in the cluster. You also need a registrator, and that's a container that will listen to Docker events and communicate them to the rest of the cluster. And you also need env console. Env console provides a convenient way to populate values from Consul into a child process environment, and it allows applications to be configured with environment variables without having knowledge about the existence of Consul. Oh, by the way, you will need a collection of 3, 5, or 7 servers running, and this is to prevent the split brain situation. Back to our various challenges. Now with microservices, each service has its own deployment workflow and its own pipeline. Deployment covers a wide range of topics. Right? We could be talking about scheduling, about continuous integration, continuous deployment, or managing build pipelines. Let's tackle these one after the other. As I mentioned, we have a couple of schedulers that we built and that are integrated with ECS. The first one is task-centric. It's very good for batch job scheduling. It's pretty much built to run short tasks. So as you have these number of tasks that you want to run as a batch, and then you'll just throw them at the cluster, have it complete, it frees up the resources, and it leaves the infrastructure ready for the next batch. This is a real natural for containers as well. Now the service scheduler on the other end can be used to maintain application availability, and it allows you to scale your containers out or in to meet your application's capacity requirements. This scheduler, the service scheduler, can take availability zones into consideration and place your tasks across AZs so as to provide higher availability. It also supports a few deployment mechanisms that we're going to describe shortly. Another great feature of the service scheduler is that if you associate a load balancer to your service, it will communicate with the ELB and deregister containers with the ELB. Basically, as you scale out the number of tasks for a service, they get added to the ELB automatically. As you scale back in, it will try to gracefully drain connections. And you can use the same ELB features that you would use with a regular EC2 instance, like health checks or grace period. One way of deploying services is by updating the task definition. This will basically roll out the new version in your cluster. And there are 2 additional configuration options for deployments. Minimum healthy % is the minimum number of healthy tasks that you want to have running during an update. Now the second one is maximum %, and that is the maximum number of tasks that you want to have running at any time during deployment. These two parameters enable you to define the deployment batch size with granularity. Let's visualize this. On this example, we have a cluster with 5 container instances, and we want to deploy using the least space in our cluster. So you can set the minimum healthy percent to a half. So at least 50% of our tasks will be healthy at any given time. Another way to look at this is basically when deploying, kill at most half of the tasks. And then maximum is 100%, so that no more than 4 tasks will be running at any time. The new version gets rolled out to 2 tasks, keeping the other 2 untouched. And once the update is successful, the deployment can move to the next set of containers. And this is pretty much like a rolling deployment. Another deployment tactic is shown here, and this one would probably be for a less resource-constrained environment, or when you want to deploy as quickly as possible. You could also perceive this as a way to do blue-green deployment. You can set the minimum to 100%, maximum to 200%. We keep our existing containers running. We add an additional 4 tasks, and we deploy in block to 4 new instances. Once the new version has been deployed, then the old task is stopped. So a quick point, something to note here. Tasks for services that do not use a load balancer are considered healthy if they are in the running state. However, tasks for services that do use a load balancers are considered healthy if they validate 2 conditions. They have to be in a running state, and the container instance it is hosted on needs to be reported as healthy by the load balancer. Another way of doing deployment is basically creating a whole new service with the new tasks running behind it with its own ELB. I like to think of this approach as a more of a canary style deployment. So you would have to use CNAMEs and our highly scalable DNS as a service called Route 53, and a specific feature of it, Route 53's weighted round robin. So you start with allocating a small percentage of your traffic to the new iteration, let's say 90 to the old, 10% to the new one, and then you watch for error rate or performance regression. And when things look okay, eventually you just route all traffic to the new service. The other side of deployments, besides worrying about schedulers and actually how you're going to roll things out, is managing multiple deployment pipelines. Each microservice will have its own build pipeline, its own test stage, its own production stage, and you have to manage all this. It can become very tedious to do on your own manually. So we're going to automate all this. So we support using any of our CI/CD partners. Here's one example on how to build and deploy a deploy pipeline, and this one is going to use Jenkins in our example. First, in this case, a developer would commit code either to code commit or GitHub. Then Jenkins would see this, getting the notification, and it would build the application from the newly updated source code. Then it would run tests on the image. Once satisfied, the image is pushed to EC2 container registry, and Jenkins can then update a running service with the new image version. ECS will simply roll out a new service based on a new task definition. Now, Jenkins is often referred to as the Swiss Army knife of build automation, and that's for a good reason. It supports a lot of AWS services via a collection of plugins. Such plugins are available for both ECS and ECR. And builds can be triggered by a webhook or via Lambda as well. Now, Jenkins is just one example. Our partners have created continuous integration, continuous deployment solutions with Amazon ECS. Worker has a tutorial on deploying a 3-tiered microservice application consisting of a simple front end, an API, and a Redis backend. CodeShip leverages their own CodeShip AWS deployment container, which lets you plug in your deployment tools without the need to include them in the testing or even production container. Selena Labs has a blog post out explaining how to configure Selena CI to trigger a build on commit and deploy to both Amazon EC2 Container Registry and ECS upon passing builds. So you'll notice that integration with our partners is available both with ECS and ECR. And Shippable is another one, by the way. Shippable is a hosted cloud platform that provides hosted continuous integration, deployment, and testing for your code, hosted in GitHub or Bitbucket repositories. In this case, hosted means that you do not have to provision additional infrastructure to build or handle deployments. It's all done for you. You can create and run Amazon ECS services and tasks on your ECS clusters from within the Shippable Formations module. You can also pull and push Docker images from Amazon ECR as part of your Shippable CI builds and deploy them with Shippable Formations across multiple clusters in Amazon ECS without ever having to manually update a task definition yourself. Shippable automatically updates your ECS task definitions with the latest image information based on your CI builds, and it either automatically deploys or you can deploy with a single click. And we are now getting into demos, or at least one. All right, so the first thing to note about this demo is that we already have a running ECS cluster. It's going to have two services running. One of them is a front end. It's an application that's written in Flask. It has a little Python application, and it's basically a hit counter. And then the backend application is a Redis container that holds the count of hits. It's a Redis service, and we're using that to illustrate the communication between the two. Also of note, on this cluster we have a Weave discovery running, and that's how the services are actually communicating, resolving each other's name through Weave. So what I'll do is I'll kick off a build by committing some code to a GitHub repository. Shippable is watching this, so Shippable will get notified. Here's how it's going to happen. Here, I'm going to commit some code on GitHub. Shippable is going to see it, and it's going to extract the code from the master branch. That code will then be brought into the Shippable build service. Shippable will then drop the build image into Amazon EC2 Container Registry, where previous versions of this artifact also live. And then it will refer to this new version when creating a new task definition and attach it to the load balancer. Now, I actually have three services running. That new service that I just described is already running at a certain version. We're just going to update the version in GitHub, and it's going to deploy the new one. I'll show you. All right, thank you, Ryan. I think we can switch to sharing my desktop now. All right. So this is the ECS console that you see here. Well, you can see how I have a few clusters running. On my next tab, I have the source code for the front end. Going back to the ECS console, if I click on the Docker, on the cluster, you can see I have three services running, as I said. One is the front end, another one is the back end. So the front end is that Python app, the other one is that Redis back end, and then I have a third service which is called deploy to ECS, which is going to be built and redeployed through Shippable. So let's take a look at, before we take a look at the source code actually, I want to show you that's the Shippable dashboard. And so this is the third service that we have. And I'm just going to update the index.html page so that we can see quickly right away that it has been updated. So how are we going to do this? Well, I'm going to find, I'm going to show you the front page first. So by clicking on my service, I can see more details about the service, and I can see that it is fronted by an Elastic Load Balancer. So I can click on this Elastic Load Balancer to get more details about it. I see that there's one instance in service. This is great. I can capture the DNS name and just paste it into my browser. Here we go. And if I do this, you can see this is the front end that I have deployed, and that has this build pipeline all automated. So the part that we will change is Pierre's startup, and right now it's in beta. And how we're going to do this? Well, we're just going to update this one line here. It says Pierre's startup beta. This is the index file. And we're going to say welcome to prod, let's say. This is saved. All I need to do at this point is commit and push my change. So I just add the change. And push. All right. While this is running, we can explore the Weave side of things. So there's something that I want to show you on the first front end. If you look inside the source code for the first front end, you see that it refers to Redis by a simple, very simple host name, Redis. And then using the same ELB tracking, I'm going to go and look at the front end from a web perspective. So I go back to my clusters, I click on the cluster that is of interest to us right now. I look at my front end. I have 3 tasks running. This is very well load balanced. And I can look at each task. And you see here, this is the name of the container that is running. It's called hit counter. If I go back to my services and I look at my backend, you'll see that for a certain task, here the container is called Redis. So let's connect to one of these container instances. As you know, all these container instances are simply an EC2 instance with the Docker daemon and an ECS agent running on them. So I can very easily SSH to them. Here we go. So I am now on one of the 3 instances that are powering this ECS cluster. And what I'm going to do is I can quickly look into what is running on this instance. Well, you can see that there are the Weave containers, and these containers are going to help identifying which service to talk to. There's also the ECS agent. The ECS agent is a container, and it will run on all of your container instances. And then there are 2 front ends here. One is the hit counter, and the other one is the one that I created and that I've deployed. So let's set up for Weave interaction, and then here's what we're going to do. We're going to try to find the IP for Redis. So what we do is we use a container called Weave ECS demo in this case that is just going to run a dig, like a DNS lookup, for a certain host name. And here the host name that we're looking for is Redis. And it's returning the IP that it has. But what if I was looking for hit counter? Then it gives me 3 IPs. And another thing to note is that if I run it again, the order should be different because it randomizes in a way to kind of load balance. All right, cool. So this was the ELD, this was the Weave service discovery part. Let's look at how my shippable pipeline is doing. It so appears that the image is still being built. Let's look at what stage it is in. It started by provisioning a node. As I said, all this build is happening without you having to actually provide an instance. It's infrastructureless from your point of view. It will boot a brand new container in order to build the application. Then it actually does the building. It is going to create a Docker image, and it is going to push it to the EC2 container service. So maybe I can show you something else in the meantime. Yes. On the shippable side, this part is the continuous integration, right? You have some code and you turn it into a finished product. But now, what about deploying it into a certain environment? Well, then you would use the pipelines. And here with the pipelines, you have it goes from CI and it goes straight into the environment through the pipeline. This is how you configure your pipeline. You will select a certain version of your pipeline definition. You define which image it is. So here we're using Amazon EC2 Container Registry, which is a highly scalable container registry that you can host very securely in that is hosted for you by AWS. So this is where I will store my most recent image, and you can auto increment every time an image gets updated. Then you can tell Shippable to just deploy it right away. And how does it deploy it? Well, it's going to look at the environments. And this is where the task is defined pretty much. And you can also specify an ELB here in routing. So the ELB will accept traffic on the port 80, but it will reroute it on port 8080 on its subscribed hosts. And on the host itself, port 8080 will turn into port 5000 into the container. All right, let's see how we're doing from a deployment pipeline perspective. We have, I think we're ready. That CI should be done. Okay, cool. So green, and then the pipeline has moved to version 32. Deployed at push 3. Okay, perfect. So if I go to this website, remember this Pierre startup beta, we modify the index the index file. And so if I reload, it should show me the different message. Perfect. Welcome to prod. This is what we committed. And this concludes the demo part. So thank you very much for attending this. Have a good rest of the day.
Thanks a lot, Pierre, for a great presentation, and to Daniele and Andrew for answering the audience's questions. If you guys have any comments on our previous and upcoming webinars or suggestions on topics you'd like to hear more about in future webinars, please email aws-webcasts@amazon.com. Again, that's aws-webcasts@amazon.com. And your feedback will help us to improve our webinar programming. Thanks again to you guys, the audience, for taking the time to join us today. Enjoy the rest of your day.